Okay, good morning, students. Sound clear? Sound clear? Please raise your hand. 跟我叫我讲话哈，来坐住。Alright, okay, thank you. Alright, so maybe you will hear a lot of the baby sound. Okay, I currently at hometown, so my brothers, all the kids here. Okay, so the chapter 6, diffractions of light. Okay, this morning we will try to discuss the two subtopics. But these two subtopics actually you already learned the concept, basic theory in the chapter 5. Alright, so the phenomena here, this is a second phenomena, diffractions of light. So in the previous chapter, okay, we focus on the concept part. So we don't really do the calculation. So we only learn the drawing. Okay, so if you recall back what you have done in the chapter 5 before this. Okay, so on the chapter 5 before this, the example diffractions of water wave. So we learned how to complete the wave ligand for the deep region and the shallow regions. So still remember the 4S concept that I told you: shallow water, slower speed, smaller angle, shorter wavelength. The 4S concept for the diffractions of water wave. So the ligand that we learned, okay, from the directions, okay, we show the normal line and then bend towards normal. Okay, so and then after that, so we have the smaller wavelength. Okay, so this is what we learn, diffractions of water wave. So under the light wave, we already learned the concept. When the light enter the optically denser medium, so the speed will be decreased as well. Because the speed decrease, so it will bend towards normal. Okay, and from the optically denser toward optically less dense, speed increase, so bend away normal. This is what we learned in the previous chapter 5. But when it comes to chapter 6, what we're going to focus now, we will learn more on the calculations. Right? So in the diffractions of water wave, we don't learn calculations. Okay, because to calculate the different depth of water, how it affects the speed of water wave, it will be complicated because the depth of water is not extremely change on the two different depth of water. But for the light, it will be easier because light, when it enter, it will be from one medium into the other medium. So there will be two different optical density medium. So from that, we will get the relationship between the change of angle. So in the previous chapter, we only learn concept. We don't include the measuring about the angle. But we cover chapter 6.1. So we're going to learn about change of angle, how to know the how much the angle will be changed, including the speed of light, how much the speed of light will be changed. Okay, so in the previous chapter, I already introduced when we mentioned about the different medium for the light, we don't comment about the mass density. We will comment about optical density. So that's why from here at the beginnings of the subtopics, it's already told you optical density not the same as a density that we define as a mass per unit volume. There is other density, which is we call it mass density. Mass density is a mass per volume, but optical density not the same. Remember, not the same. All right. So, basically, we're talking about optical density. It's just talking about the properties of the light, how it affected by this medium. Okay, so this is what we call use the term optical density. So when you explain it, make sure you use the term optically denser or optically less dense. Okay, so here's an example. As I told you before this, we already learned in the chapter 5. Okay, so when it comes to the this chapter 6, we're going to learn first one. This term we call it diffractive index. If you still remember what we have done before in our Ujang Amani science, So you already conducted the experiments. After from the experiment, you study the relationship between the sin I and sin R. From that, I ask you to determine the gradients of the graph. So the gradient of the graph is a sin I over sin R is presenting the differential index of the medium. So this differential index is symbol as N. Right? So with the C over V. Right? C is the speed of light in vacuum. Remember, this speed of light in vacuum is a constant value. Speed of light in vacuum is actually constant value, which is 3 times 10 power 8 meter per second. So in this calculation about differential index, we have a few formula referring to the same finding differential index, and then there's a two different C here. When you look at the list of formula during the exam, okay, so example, you look at this formula list, right? Okay, so for the chapter 5 here, so this is follow the SPN standard lah, as I repeated many times. So from here you can see all here are looking for the differential index. So this is what we done just now, which is a speed of light in vacuum over the speed of light in the medium. And then we have a sin I over sin R here. Remember, when we apply this one, N equals sin I over sin R. The anchor I must be anchor that we taken at the vacuum or medium, or A. And then the R must be the medium. So let's say the R is a medium X. Then the differential index, here's the differential index X. Okay, and then we have another C here, 1 over sin C. This C and this C is not the same. This C is a critical anchor. This one is a critical anchor. We will learn in the 6.2. Right, so remember this C is not the speed of light in vacuum. Okay, and then here is actual depth over the apparent depth. So all these are the formula we can apply, and included here this one, N1 sin theta 1, N2 sin theta 2. So this is the one that we call it Snell's law. So this one, after we simplify it, it become this. Actually, it's the same formula. They are the same formula. So now we're going to slowly to look through it, how we're going to change this formula number 6 into number 2 formula. All right, here are the example for the different differential index. All right, so in the vacuum or A, differential index is 1. So this is the lowest optical density. This is the lowest optical density vacuum and A. So from here, you should keep in your mind, we never have the differential index of the particular medium less than 1. The smallest differential index is 1.00. Once you calculate the differential index less than 1, means that substitutions of formula is already wrong. So please keep in your mind, we never have a differential index less than 1. Okay, and then even most of the time you can expecting that denser the medium, optical density will be higher. But not all the time. All right. So basically, most of the medium, if the mass density is higher, optical density also higher for most of the medium, but not all. Due to that, we must only mention optical density. We must include the term optical. All right. So so later I will continue to discuss about this part. Okay. Because sometimes the example it will show that when you have a denser medium, is also indicate the optical density is increased. All right. So the one is some special case I will tell you later. Okay. So now we're talking about the Snell's law. Snell's law is the ones to delay between the anchor and the differential index of the medium. So example here, we have the cases water to the perspex, water to the glass, water to the diamond. So all have the same incident angle, all have the same incident angle. And then from the water, 1.33. Okay, when you enter the difference optical density medium, we get a different result. So this is a diffraction index of the different medium, N2. Okay, from the result showing here, we come out the conclusions. We have a Snell's law to delete all these diffraction index and the anchor. Okay, from the experimental result. So we have the N1 sin theta 1 equal N2 sin theta 2. And this one, as I mentioned just now, this one actually also equal to the N equal to the sin I over sin R. When we simplify it, and then this one, even we simplify it, you must remember it must apply in between A or vacuum. So it means that if you want to apply N equal to sin I over sin R, you cannot apply here. N equal to sin I over sin R, this one, you cannot apply for the cases all here. Because the cases here are between water and other medium. Water and others medium. It's not between the water and A. If water and A or the others medium, perspex with the A, glass with the A, diamond with the A, yes, you can apply this formula. But it's between water and others medium, not the A, you cannot apply this one. Okay, you have to apply Snell's law. Okay, why this formula have a special term and condition? Actually, it's already explained. Where is it? It's already explained here. This one. So from the formula itself, you see, if N1 sin theta 1 equal to N2 sin theta 2. So when we rearrange it, we have the N2 over N1. It will be equal to the sin theta 1 over sin theta 2. Okay, here's the N1 sin theta 1. Okay. So in this case, if the medium one is the A, 1.00, which is the medium is the A or vacuum. So in the case here, this theta, it must be angle that we measure from the A or vacuum. Therefore, because number N2 divided N1 is the diffraction index of A and vacuum, so it's equal to 1. Therefore, the formula, it can be simplified as this. Because divided 1, we don't need to show. Okay, so due to that, when we simplify the Snell's law formula, it becomes N equals sin I over sin R. They have a turning condition. The angle I or incident angle, it must be referring to the A or vacuum. So in the old syllabus, actually, they don't learn Snell's law as this. In old syllabus, we are not introduced Snell's law as this one. In the old syllabus, we introduced Snell's law as N equal to sin I over sin R in the old syllabus. And because of that, the student actually, what they learn is not complete. So especially when the question given like the example like this, students normally they will do wrongly. Okay, because they don't really understand the equation fully. Okay, so hopefully that you understand the formula between these two. So now look at the module here. Okay, so I already shared it before for 1 week already. So hopefully that you already print it out or use a soft copy. So anyway, when the school open later, I will give you the hard copy lah. All right. So hopefully you already fill out the answer. So this one. Okay, light always travel in straight line lah. Okay, even through the transparent or the partially transparent material, it also will travel straight line. But when there is a change of the speed, then it will cause a diffraction phenomena to be occurred. Therefore, the direction of light close a boundary between the two material with a different optical density, it will bend. So when the light travel from the less than, so this one please add the terms here, sorry for the mistake. For the optically less than medium, into an optically denser medium. Same also for the diagram here lah. So add the term optically less than medium, optically denser medium. Right. So I want to edit a forgotten already. Okay, so it will be when you go into the optically denser, it will become slower. When slower, it will have a small angle. When have a small angle, it will bend towards normal. Okay, and vice versa for the different opposite cases lah. Okay, so the law of refractions of light. Okay, so this one in your textbook it is not introduced. The law of refractions of light it doesn't introduce about the diffraction index. Under the law of refractions of light, it just only told you that sin I over sin out is always a constant. It doesn't tell you this constant value is what. Right? Under the law of diffraction. Just only the sin I over sin out is a constant. So it means when you apply the law of diffractions, the meaning is, let's say here, I have this angle I1 compared to angle R1. And then later, if I have another case with a different I, let's say I have the I2. Here I have the other case I2. So this I2, different angle bigger. So bigger I2. Then for definitely I will have another bigger R2. So bigger R2. So the relationship between the change of angle here, we can apply the law of diffraction, which is we use the sin I1 over the sin R1 equal to the sin I2 over the sin R2. So because it always equal constant value, so that's why when the cases change, it will still equal because must equal constant. Okay, so when we apply the law of diffraction of light, we don't need to care whether the light is traveling from the optically denser toward optically dense lens, or it must be from the A into the any particular medium. We don't need to care about that. As long as there is a meanings of light, we can apply this sin I over sin I equal constant. We can solve it for the same between two medium on the different angle cases. Okay, but once you apply the Snell's law, or when you apply Snell's law, it will include the concept we call diffraction index, which is have the n here is a diffraction index. So you must be knowing about the diffraction index of the particular medium, then only you can substitute the Snell's law. But when you apply the simplified formula, n equals sin I over sin r, this one, the angle I here must be the angle in the vacuum. So it cannot be any other two medium. One of the medium must be vacuum or A. That is when we apply the simplified formula. Okay. As I mentioned just now, if the diffraction index of the partially transparent material, it must always larger than 1. Because smaller equal to 1 is the A or vacuum. Okay, here are the others formula we already know, except the last case here is a deal depth and pendant depth. So this one later we will learn we will learn how to draw the ray diagram as well for the deal depth and pendant depth. Okay. So and then the number 3 here. So please the next here, please do some calculation, practice the formula for this number 3. Okay. So once you're done, please share your answer in the message box here. All right. So I wait for you to share the answer. Alright, can someone share the reflecting index of the liquid X is what? Okay, faster. No one should answer. No one should answer. Then I will just hang here. Alright, so one more thing I forgot to tell you. Usually, reflecting index, we will give 2 decimal places. Just like you referring to a textbook, you see here. So in the table 6.1, so you see all the 2 decimal places. Usually, we will show the 2 decimal places. Even there is a reflecting index of A or vacuum, is 1, we will write 1.00. Okay. So for the first one, okay, 1.44. Is it perfect 1.4, 1.44? But my answer is 1.45. Since 65 since divided by 39. So 1.440. So it's 1.44. So my answer is wrong. Okay, 1.44. Okay, how about the reflecting index of the medium Y? Reflecting index of medium Y is 1.40. All right. Okay, so the next one, anchor R, anchor I. Given that medium defective index 1.55, so it's traveling from A enter the medium, and from the medium enter into the A again. So the anchor of R is what? $31.72. Is there any other answer? All agree with the answer 21.72 given by the early. $31.72. Is this correct? So 21.72 is correct. If someone you get answer is more than that, 30 plus, so your answer is wrong. Okay, so 21.72 or okay, and then the anchor I will be 35. Okay. So please remember this 55. This is not the anchor I. Angle I must be anchor stick to the normal line. Angle I must be anchor stick to normal line. So here the angle I will be equal to 35 degree. So and then why the angle I here is 35 we know. Okay, just remember here. As long as there is a parallel borderline, no matter in between we got how many different medium, as long as it come out against is a parallel with the borderline before, as long as these two are parallel borderline, and then it's a same medium, so the angle I, this angle must be equal. These two angles must be equal. Okay, even inside it may have bend towards normal, bend towards normal, bend towards normal, bend towards normal, bend towards normal. At the end, it came out, it's still referring to same angle, right? So as long as they are the parallel borderline. Okay, so just take note for this. So that's why we know that the angle I at the bottom here is 35 degree. Okay, so okay, then next one here. Okay, so this is how we draw the diagram to show the positions of the image. So quite similar to the chapter 5 that we learned, but chapter 5 actually we don't really focus on this. Chapter 5 we focus on the diffractions of water wave. So and then about the light wave, so or the light ray, we will learn in detail in the chapter 6 lah. So now we're going to learn this one. Okay, for this light game, actually we have another better way to learn. Who just coming? Emitted already, yeah? Or left already? Okay. So for regarding this light game, okay, first thing you have to remember, image object always at how to say that, the image always upright above the object, so it will be on the upper position here above the object. So when you show the image, it must showing between the same borderline. So even if you maybe you show slightly outside here, even you show slightly outside here like this, so as long as it's still between the borderline, it's still accepted lah. It's still accepted. Alright. So but better that you show already above, exactly above the object is better. Okay. So this keep in your mind. So in our drawing, actually you can make it very simple. So let me show you about here. So let's say this is a water. Here's the water. And then I have a fish here. Okay. So you make the one's reference point. Let's say we take the eyes of the fish as a reference point. Okay. So here is an image of the fish. Therefore, from here, we draw one straight line. One straight line from the objects to the image. Go straight forward upwards. Here. Go straight line upwards. Okay, this one, why it can be go straight line? Because it's parallel with the normal line. So which is the angle I here equal to 0. Then for the angle R in the A also equal to 0. This is the first one straight line you draw. Okay, and then afterwards, second straight line. Your eye, let's say your eye is here. So the second straight line is from the image. From the image is the one that we see. So that's why from the image, we draw straight line directly into the eyes. Okay, directly into the eye from the image. I repeat again. First straight line for object, link to the image and go straight forwards. Okay. Second straight line from the image into the eye. And then afterward, at the connection point between the borderline between the water and the air. So here we link to the object, straight line. Okay. From this divider point here, we link it into the object. Okay. So for that, yeah. Okay, go straight line. Hold on. Why hang already? Give me 2 seconds. Okay. So like this. Then here we can see the concept here. Normal line. This is an incident anchor. Here is an incident anchor. And then here's a deflected anchor. So from the ligand, you can see it will be deflected away normal. So one of the past year question in SPM, the year a bit special. I think purposely do so. The year SPM, it gives the image as a student show object. It gives image as a student show object. So you just have to keep in your mind, image or above object, then object will be below image lah. Alright. So you just need to reverse the drawing method. Then it can be done already. Okay. So now you practice with the next light game. So like this one, how we going to show the image? It's a position of eye is upright. Okay. So how are you going to complete the light game? So you don't need to care where is the positions of the eyes. Right? You just need to follow the methods, okay, to complete the light game. So first get the one reference point. First one, okay, let's say you take the bottom here as a reference point. You take the bottom here as a reference point. Let's say this is one. Okay, what you need to do is from here, you use a ruler, draw one straight line forwards. Go up. Go up. Okay, use a ruler lah. Use ruler please. Use ruler. I erase it. Okay, show the image first. Show the image first. Okay, here. Okay, so for the case here, okay, we get another one's similar image first. So this is a similar size image. Okay, so from the same reference point, so let's say we fix a reference point here, reference point. Okay, and we draw one straight line. From here, one straight line go upwards. Okay, so this is one straight line. Okay, for object, image, and after the eyes. So go straight forward. Okay, go straight upwards here. Okay, so the next is another straight line. Another straight line from the image. From the image to the eyes, right? If the eyes here, so never mind, we go slightly to the left or slightly to the right, doesn't matter. Okay, slightly to the left here or slightly to the right here. Up to you lah. Okay, so like example, we make it slightly to the right. Yeah. Okay, slightly to the right. It's a straight line. Okay. So straight line. And from the borderline touching here, okay, we connected from here to the object. So like this. Okay. Okay, so connect here. So it's like this. Then the light game is done already. So from here, if you want to show the anchor, so get the normal line here. This is your anchor. Incident anchor eye. Deflected anchor out. So, and then in this case, our calculation, if we want to apply, let's say this is a water, right? So deflected index of water, we should apply this. Sin out over sin I. Why we have to apply this? Because this anchor R, which is here, this anchor R actually is an anchor in the A. That's why we must put it on top. So we don't really blindly follow the symbol in the formula, which is the I over R. You have to look at the situations. Because the formula N equal to the sin I over sin R, the angle I here is the angle referring to the A medium or the vacuum. So it means that we are basically referring from the light travel from the optically less dense into optically denser. But when for the case like this, the image is forming when the light is travel from the optically denser into optically less dense. So we don't really follow the symbol. We apply the concept. Then when you do a calculation, will be like this. Or the other calculation we can make is this is our deal depth from this position. This is our deal depth, and here will be apparent depth. So the refractive index also can be from the deal depth over apparent depth. It should be equal answer lah. These two should be equal answer. Okay. So, but when we in the drawing itself, we no need to do calculations and measure the change of the depth exactly to make the correct of the ligand. When we're drawing, we no need to care about the actual calculation because there's no that much marks for the complete the ligand. Ligand we just apply concept. It's just like happened in the chapter 5. But when the calculation one, it will be focused on calculations. So we don't mix calculation and the ligand together. So this part you don't worry lah. So we don't ask that much step from the one questions. Okay. So now, so find 2 here. Okay, how much the apparent depth? Right, so I give you the actual depth 4 meter. Then how much the apparent depth? Just substitute formulas. So I think there's not challenging at all. Anyway, just give me your answer. How much is the apparent depth for the image form? Others all online and back to sleep already. You diam-diam jangan bising So it's 3 or 3.01? Which answer we should give? 3 or 3.01? So it's a 4 divided 1.33, right? So the answer is when you use it, 1.33. So answer is 3.0075. So for me, the better answer for nowadays SPM 3.01 is the last time SPM. 3.01 is the last time SPM. Nowadays SPM is better for me, right? Safer answer is 3.008. Safer answer is 3.008. Okay, so we don't round off, only give 3, or we give 3.01. It's better the answer like this, like 3.0075, 18797. So it's better that you give 3 decimal places answer. 3.008. Safer lah. Okay, 3.008 meter. Okay, so number 6 is apply the formula, another differential formula, which is using the speed of light in vacuum comparing to the ratio toward the speed of light in the medium. Okay, so this one just a substitute formulas only lah. Possibility asked in SPA is very, very, very low because not challenging at all. It just blindly substitute formula can get answers already. So anyway, what's the answer? So the refractive index X, medium X, it should be liquid X is how much the refractive index of the liquid X? Don't want to give answer. Right, so 2.00. Okay, thank you. Okay, so number 7 is quite challenging. Number 7, this question actually is the question in the old syllabus textbook. So in the old syllabus textbooks, all right. So the time, as I mentioned, as I said that, the time because we don't introduce the real of the Snell's law, we just only introduce a simple formula. So many students, this question they will do wrongly. Okay, so I not need. Okay, you can draw it later. So you can use a potato to draw complete the diagram later. Now I just want you to focus to tell me the answer lah. So as you know, when you enter the water, it will bend towards normal. It will bend towards normal. And the grass plot, so the 15 days of water 1.33. The 15 days of grass 1.5. So it means that grass is optically denser than water. So means that when the water from the water into the glass, it will bend more towards normal lah. Right? Because it's from the optical index length into water. So the fatty index is 1.33 here, and the fatty index is 1.50. Okay, so the fatty index is 1.50. So that's why it will bend more towards normal. Okay, so now I need you to tell me how much of this anchor A and the anchor B. So I want to know about the anchor A and anchor B. So please calculate for me how much the anchor A and how much is the anchor B. Alright, so I wait for your answer. Already your angle B is wrong already. Jasmine? Anyone can give me correct answer for angle B? Right. So for determine the angle B, if you apply 1.5 equal to the sin angle A over the sin B, if you apply this, it's wrong because angle A is in the water, not in the A. Because of that, 1.5 is wrong. If you want to apply sin A over sin B, you should make equal to 1.5 divided 1.33, which is you should apply the Snell's law. 1.33 sin theta sin angle A equal to 1.5 sin B. Right? Okay, so this is the one. This one. Okay, so for the Snell's law. Okay, so if you want to find that sin A over sin B with n equal to the sin I over sin R, you should apply 1.5 equal to the sin 45 over sin B. So if you apply this, yes, you will get the same answer angle B. If you apply 1.5 equal to the sin 45 over sin B, you will get same answer for the B, because when the B came out into the air again, so it will back to here 45 degree. Then this is the angle B. So with this, then you can apply n equal to sin I over sin R. So sin 45 over sin B, you will get the same answer 28.13. Okay, so thank you for Mira, your answer. Okay. So is it okay or not for this question? If yes, please raise your hand. Okay, so hopefully that you learn from the mistake. Okay, SPN, they always like to ask questions like this. First one, it may give you the between the two different medium, and then some students, they will apply wrong formula, or they will ask you the question like this one, then it will cause you to apply the wrong angle. So just be alert for these two common questions we'll ask in SPM. Between two medium, no included the air or vacuum, or it gives you the angle is not the angle of stick to the normal line. Then it's a wrong angle. You cannot apply in the formula. So just alert about these two. Okay. So I think that's all for the 6.1. Let's see, is there anything else I want to discuss with you? Okay. So so in the textbook, okay, here regarding the dear depth and pattern depth. So please look at these two diagrams in the textbook page 238. Page 238 for this figure 6.11 and figure 6.12. So this two is very good for you to learn. Okay, because usually we will always focus on that showing the image on the inside the optically denser medium. And nowadays, this textbook, especially as figure 6.12, is another one good thing for you to think about it, which is that we forming the image on the optically less than medium, which is that we view inside the optically denser. So because of this, then the formula you see, this is the real height. This one is our real height. And then this is a apparent height. So your diffractive index here, okay, actually when we apply the formula, right, we have n equal to the hash over hash, right? So in this case, if you use a hash over hash, you will get answer n is less than 1.00, less than 1. Because you have the smaller value divided by bigger value. The apparent depth, which is the height for the image, it will be bigger than the height of the object. So our diffractive index will be less than 1.00. Why? Because what we calculate here is a 1 diffractive index of the A over the diffractive index of water. So that's why it's a 1 over 1.33. Okay, and then the case here, this is our deal depth on the figure 6.11. And then this is our apparent depth. So this one will be diffractive index of water equal to the deal depth over apparent depth. This is no issue because this is normal case due to over the diffractive index of this one in the A. So this is A. This is no, not A. So sorry. All right. So okay, it divided 1.00. Okay, so this is a special case. So since that it gives you already the figure for you to think about this, okay, so meaning that in SPM they haven't focused on this part yet, which is the substitution of the formula n equal to hash over hash is in the reverse way. So please take note for this. I worry that the coming SPM, either paper 1, it will be have a question for this one. So once you blindly apply the formula, then you will get the wrong answer. Just be alert lah, which is we never have the diffractive index of the any medium will be less than 1. So in this case, our answer actually is not the n here. Our answer actually has a 1 over diffractive index of water. Okay, so just take note about this one. Okay, and regarding the experiments, okay, so this is the one that we conducted in our Form 4 final year, okay, Ujian Marine Science. Okay, so hopefully that you still remember what you did. Okay, just only the difference if we don't really use a red box, we use a pins to identify the positions, which is all it will be aligned because when the light is bending, so when we make a line, so it means that we follow the bendings of light. So we see the object still we see the image still in the straight line. That's why I use the pins to make overlapping each other so that make it align it so it's a straight line. So from there we know how the light is bending. Okay, so this experiment actually we can conduct it. Okay, so we can conduct it with a semicircular glass block. Okay, we can conduct it with a semicircular glass block. The difference is, okay, so this is the one we conduct with the rectangular glass block. Okay. Similar experiment, it will become easier if we conduct it with the rectangular glass block, semicircular glass block, sorry. Okay. If you still remember when the time you conducted this experiment with the rectangular glass block, okay, so you have to draw on the paper you have to draw on the paper, it will have a different position. Okay, it will have a different position. Okay, so from here, you're going to measure one by one what is their defective, what is the defected angle here. Okay, what's the defected angle? Or actually measure here is the same. What is the defected angle? So it will be came out from the glass floor on the different position. But if we conducted with the semicircle glass floor, when you're changing your incident ray, so let's say point the center here, this is the normal line. So when you have the difference incident angle, okay, let's say like this. So the result all will be concentrated here. It will come out, go straight line. All will be straight line. Okay. So it will be, all here will be straight line. So means that if we on the paper, if this is your A4 paper, so on the A4 paper, you can show the one big protector diagram, which is this big protector diagram is already have the anchor show on the paper. So you no need to remove the glass block. Immediately, you can study, if you use a light ray, immediately you can study how much the anchor. Okay, so you no need to remove the glass block because it doesn't bend away. At here, it doesn't bend away. It will go straight line if you use a semicircle glass block, because for the circle, when every light pass through the center of the circle, so actually here is a perpendicular with the surface. Every single point here is perpendicular with the curved surface here. So that's why when the light pass through the center for the semicircle glass block, right, when the light enter to the center point here, and from the center go to the edge of the curved circle here, it will go straight because here is parallel. This one is parallel with the normal line. So the incident angle here is 0 degree. You will make the deflector here also 0 degree. So that's why the light will be just came out straight line. It wasn't bent away. So you no need to like the rectangular glass block, right? So when you have the result here, so the result come out here, and then you have to remove. After you remove, then only you connect. Then only you can measure the angle. Like this one, for the semicircle glass block, from the result here, you can, if you have the protector ligand at the bottom, you can straight away study the angles already. You don't need to link the line. This one, you cannot put the protector angle here to study angle because this line and this line is not straight. So you have to connect this point and this point. You connect, you only can measure the deflected angle. So the step will be more comparing using the semicircle glass block. So there's a slightly difference between these two. But at the end, if you're using the same medium, both glass is the same glass, the result will be the same. Only the procedure slightly different. Right, so this is regarding this experiment. Okay, so when we plot the graph sin I against sin R, so the graph we plot, okay, we have the two graph can be plotted here. Graph of R against I and the graph of sin I against sin R. So for this graph, it came out in the UAS, Ujjayi Science SPM 2022. So, okay, many, I think nearly all the teachers don't expecting us asking about plotting this graph because this graph is a curved line graph. Only the sin I against sin R, it will be straight line. Okay, when the R against I, the graph will be curved. Okay, it will be curved at the edge. If your R against I here, so the graph will be curved at the ending part. Okay, so due to that, that's why this year this year I told the Form 5 student, I told that this year you over already is already proved. But before that, I already told them very high possibility you will ask the student to plot curve line graph, because the year before they already tried one time. So this year, that's why they want to make sure everyone can draw. So that's why it came out the experiment to plot the curve line graph. And then the just over one is real. Okay, is as our expecting it as a plot curve line graph. So for the next year coming Ujia Armani science, so later I think about it, see what is a possible question will be asked. I think the possible question it may this one. I think this one. Okay, determine the diffusion index of water using the non-parallax method. Because the apparatus is very simple and easier. Only the difficult is the technique. Technique how you study result. This is a challenging to get the accurate result. But the experiment is very simple, set apparatus. Even now, later you can try at home. As long as you have a one transparent container, like example, let's say you have the Coca-Cola, Pepsi, 100 plus, 1.5 liter bottle, you can use it. Just cut it in like the the long beaker. So then you can do the experiments already. Okay. So in the bottom, you can put a pins as an object, or is the bottom is a transparent, you don't need to put a pin at the bottom, it's just on the paper. You get a paper here. So on the paper, you draw a line, thicker line, and then after that, you put a container here. So you put a container here, right, and then fill the water. So from the water, when you view from the top, you can see the bottom line as the objects already. Okay. So what to do is when you fill the water, so from the water itself, you measure there is a real depth of water. So you just get a pin or get a pen. So you start to move. Okay. You change the positions of eyes. So you view at the edge here. You view at the edge here. So and then your hand make a. So sorry, the mark is on the other side. Wrong side already. So are you ready this one? Okay. So this is dear depth. Okay, so and then your eyes just at the edge here. So you hand putting the pens here, pointing the pen. Okay, so and then you slowly move upwards, vertically upwards, until from the top view, this is the line inside the bottle, and then the pen outside here. From the beginning, it's not a line. So even you put a line here, but from the top view, it's not a line. So then you have to move upwards until you see there's exactly a line. When exactly aligns already, so your eye position, you try to move forward, backwards here. So it means it's slightly view from the left, slightly view from the right. If you still see there's a line, then means that there is non-parallax vector. So the position is correct. If you slightly move forward, backwards, okay, which is the view from the side of the line itself, you see there's not a line, that means the position is incorrect. You have to slightly up or slightly down a bit to check. Not only perpendicular upwards, you have to be slightly left, slightly right to see whether it still aligns or not on the position. If align, then this position you mark there. So after that, you measure, there will be the pattern depth. So when you use the actual depth over the apparent depth, so it will be equal to the effectiveness of water. So the answer will be almost equal to 1.33. So if you get the result plus minus 0.0, I guess 0.05, I think it's still acceptable. Okay, so I tried a few times already. It's quite easy to get around 1.32, right? So you have to practice the skill. This one, maybe later when open school come back, I think I will conduct one experiment for this one for you to try your skill. All right. And then once it's done already, then we change the depth. So it means that this experiment, we're going to repeat it by the different actual depth with the different apparent depth. So like this one. All right, so deal depth 6 centimeter high, 7, 8, 9, 10. So and then after measure the apparent, measure the y from the bottom and then minus it. So use the actual depth minus the y, get the apparent depth as given mentioned here. So after that, we plot the graph, it will be straight line. Then gradients of the graph, it should be directly proportional lah. So gradient of the graph will be presenting the deflecting index of water lah. Okay. So this experiment is very easier and simple, but it needs a very high skill of the experimental skill. All right. So that's why I think there's a quite possible it will ask within these 3 years experiment. Okay, so the other calculation just now we practiced already. So the example 1, 2, and 1 and 2 here, you can just go through, read only lah. And then formative practice 6.1. So all these questions similar to what we practiced just now. Okay, so you can just go through it. I will discuss it later lah. Okay, so now 6.2, total internal diffractions. Okay, total internal diffractions. Okay, then you watch the one video first. Okay, so now I adjust the brightness already. Can you see this line? Okay, this is a line here. Can see, right? So if I move it away, so you see the line, right? This one. Okay, so when you look at this line, you see the angle here compared to the line, this line. This angle actually they are equal. Okay, means that here what happened here? This is a diffractions, but it's internal diffractions. Okay, and what happened here? This angle and this angle, this is a diffraction. Okay, so here is away normal because it's optically less lens in the A. So this one inside the glass, optically lenser. So here inside the glass. Okay, but at the same time, we can see the internal reflection. So later I will replay the video. Try to observe what happened. What happened to the brightness of this internal diffractions rate. Try to see the brightness. Focus on the brightness. So I think you can see getting brighter and brighter, and outside here getting dimmer, and now missing, no more. So then here, so now the brightness, okay, is almost equal already. By right, it should be equal lah. So this one, okay, we call it total internal diffractions at this moment. Okay, so after that, even if we increase further the angle, there will be no more any light outside here, because now it's total internal diffractions. So they got no any more light reflected outside. Okay, so the moment before before we get the total internal diffractions, what we can see is the angle of diffracted ray out from the glass so what we can see is when the moment we slowly increase this angle I, the moment we slowly increase this angle I, then angle out definitely will be increased also. And we come to the one moment, the angle I will increase further. We increase further the angle I until the moment this angle here become 90 degree, which is this light ray, it come to the borderline here. It come to the borderline here. So this moment we get the 90 degree for our diffracted angle. This angle I, we call it as angle C, which is critical angle. Because once our incident angle in the glass block more than critical angle, okay, then the inside here, it will be same angle on the other side, and this one is the total internal deflection. Okay, so before that we have internal diffraction, but it's not the total. Means that the portions of light, some is diffracted inside the glass floor, we call it internal diffraction. Some is diffracted outside the glass, bend away normal. When the bend away normal outside the glass come to the 90 degree, that is a critical moment, because after that it have no more angle can be increased further, because after that once more than 90 degree it will coming into the glass. Then there is a moment that total internal diffractions occur. Right. So before we come to the total internal diffraction occur, the angle make the diffracted angle 90 degree. This angle we call it critical angle. So once more than critical angle, total internal diffraction occur. Less than critical angle, we still have the diffracted angle outside here, diffracted away normal, and then it doesn't mean that we don't have the internal diffraction. We still have the internal diffraction, just only the internal diffraction is not the total 100%. Okay, so that's why the ligand you can see like this. So this is a moment. So this is a moment. You have the internal diffraction, this one. You got the internal diffractions here. You got the internal diffraction here, but it's not the total yet. Internal diffraction, but not total yet. Okay, you can maybe can say this one is only 10%. 10% of the brightness and then 90% outside here, example lah. So because most of the light is still diffracted outside, only partially the light is diffracted inside. Okay, so this is why both angle of diffraction, angle of deflection, both is using the same symbol R. Alright, so but hopefully that you don't confuse lah. Okay, between these two angle, there are two different phenomena here. So when referring to the knots here, so this is the one I already explained to you. So now you try go through the knots and fill out the blank and try to understand the content, the explanation that I just give you. Okay. So to let total internal diffraction occur, not only focus on the critical angle, another one most importantly is what? The light must be travel from optically denser to optically less than medium. Because only with that, our angle R in the less than medium will getting bigger and bigger until come to the maximum 90 degree. This is only happen when the light travel from optically less than toward optically dense. Optically denser toward optically less dense. Only the angle will be bigger. Angle R will be bigger than angle I. So that's why when we increase the angle I further, it will make the R big until the moment R become 90 degree, we still have the angle I inside the optical denser medium. So if we get the R equal 90 degree, then the angle I in the optical denser medium is the one we call it critical angle. So once the angle in the optical denser medium bigger than critical angle, so the total internal diffractions occur. Okay. So when we apply the formula, so we will have, okay, because before this, we apply the simple formula. So remember, this is the medium X, and then the sin I, this must be the angle in the A, over the angle R in the medium X. So when the moment angle in the A is 90 degree, so the angle R inside the medium, we call it critical angle. So that's why it becomes sin 90 degree over sin C. Then the sin 90 degree is equal to 1. So it's a 1 over sin C is the one to determine the diffractive index of the medium. Or when we know the diffractive index of the particular medium, we can use n equal to 1 over sin C to determine the critical angle of the medium. Okay? So, that is once. Okay. In the textbook also given us exactly the same thing, so you can read through to make yourself more understanding. Okay, so here's a substitution of formulas, how we express n equals sin 1 over sin C, and then the C, remember, this is not the speed of light in the vacuum. This C is the critical angle, right? So now, according to this concept, I want to ask you, to let the total internal diffraction easily occur, I repeat again, if we want to let the total internal diffractions easily occur for the particular medium, the diffracting index of the medium is higher or lower? I repeat again. Diffracting index of the medium higher or lower will be easily to occur total internal diffractions. Is higher diffracting index easily occur total internal diffractions, or lower diffracting index easily occur total internal reflection? Which one? Higher end or lower end will have easily occur total internal reflections? Is higher refractive index will be easily occur total internal reflections or lower refractive index? Okay, so alright. So it's a higher refractive index will be easily occur total internal reflections. Okay, because why easily occur total internal reflection for a higher refractive index medium? Because of what? Why higher total internal why higher refractive index will be easily occur total internal reflections? Because of what? Because they have a lower C. They have a lower or smaller critical angle. When the critical angle is smaller, so it means that incident angle, okay, will be easily more than critical angle. Right, once the incident angle easily more than critical angle, so total internal reflection can be occurred. Right, so that is the question always asked in SPM lah for this subtopics. Okay. So okay, so now look at the 7 here. Number 7 here, try to find the angle Y to determine the effectiveness of the medium and determine the angle Y. So after this, we only left phenomena or the application of the total internal reflection. Then we finish already these subtopics. So the next class can be focused on the lenses. So 6.3, 6.4, I don't know why I have divided another subtopic 6.4. Because for me, 6.4, it should be part of the 6.3. Okay, so anyway, I will these two will be covered together lah. Okay, because for me 6.4 is just a specific focus on the formula. Okay, so I think we need another 2 more lessons that we can finish the chapter 6 already. Okay, so now please give me the answer for this defective index of the medium and also the angle Y for this number 7s. Faster. Defectiveness of medium. No one ah. Okay, so Mira 1.35. Let me calculate. Is this correct? 1.35. Okay, yes, 1.35. Correct. So for those that don't know how to get 1.35, please look at this diagram. You have the diffracted ray here, which is this one. This is your 90-degree diffracted angle. So it means that inside here, this one's a normal line. So this angle is your critical angle. So critical angle is equal to 48 degree. So based on this triangle lah. So you have the 42 here, 90. So here one must be 48 lah. So that's why the diffractive index will equal to 1 over sin 48. So that's why it's 1.35. So how about the angle Y? So the angle Y, so the suggest answer 25, okay, yeah, 25 degree lah. Okay, so when you apply the formula, after you know about the 1.35 diffractive index, when you apply the formula, you will get this angle first, the angle, incident angle lah. So which is sin I over sin 42 here is equal to diffractive index 1.35. But the Y is on the other side. Okay, so that's why you have to use 90 degree minus the angle I. They only can get the Y. So Y is 25 degree. So I don't encourage you to substitute all this all together into the formula lah. So I encourage you to find the angle I first. From the angle I already, and then use the 90 degree minus the angle I to get the Y angle. Step by step you do lah, slowly. So it's better lah. Then get the 25 degree here. Okay, so for the phenomena that involve the total internal diffractions, the first one is very common one we can see in even in our daily life also can see with this one we call it mirage. Okay, so if you're referring to a textbook, you see the mirage here. Huh? If you're referring to a textbook, okay, so this photo behind here, this one is the one we call it mirage. when on the one straight line, straight road during the very hot weather time, you will see right at the far ends of the straight road, you will see that the virtual image like similar. You see there's a pool of water, right? So this is the one we call it mirage. It's a virtual image due to the formations by the total internal diffractions. Okay, so the explanation given in this diagram, maybe it's not the cloud, maybe it's something else far away. Okay, just like in my module, I show you there's a coconut tree example. It's very far away, so by right, we should see that this coconut tree far away. We should travel in straight line. Then we see this coconut trees here, but we doesn't see the coconut trees there. Okay, it's bring by the light bending into our eyes, because it's on the position. It's not on the straight line that we view. It's on the others positions. So just because of bendings of light, it bring it enter into our eyes. So our eyes we see in the straight line. So we see the image appear here. But it's not a clear image. Depends on the conditions lah. Most of the time we don't really see it's very clear. Okay, but sometimes it really can see very sharp and very clear virtual image. Okay, so this one, this mirror actually in the Mandarin we call it 海市蜃楼, right? So it's something that it will just like happen in the, I think this year got 2-3 times reported. They see a building appear on above the sea. So actually that one is a virtual image because of this mirage. The building is not appear the sea. The building appear the sea because it's the image bring by this total internal reflections. Okay, and usually it will be upside down. Okay, usually it will be upside down. That's why the people say that is a sky building, right? So actually because of the bendings of light, how the light can be bent in that way. All right. So if you refer in textbook, because that during the very hot weather time, our A layer have a different temperature. So the layer close to the ground is a hotter area. Above the higher altitude will be cooler. So when the light traveling from the cooler toward hotter, which is a denser toward less dense, so it will bend away normal. When bend away normal, so it will come to a moment the angle will be more than critical angle, so total internal reflection occurred. That is the moment at number 2. Total internal reflection occurs. So that's why the light will be bent upwards. When it bend upwards, so always bend away normal, and then at the end it coming into our eye. So in the eye we see there is a straight line, so it's appear the image here. The image will be the virtual image. Okay. So this is what happens on the mirage. Okay. And then the formations of rainbow. Formation of rainbow actually there's a 3 phenomena. Formation of rainbow actually consists of 3 phenomena. First one is the diffractions. This is a new dispersion. And the last one, total internal diffractions. Okay. The first phenomena here is a moment when the light, sun ray from the air enter the water droplets. So when the light ray enter the water droplets, so here's a normal line, then it will bend towards normal. This is the first, right? The light ray, here's a normal line, it will bend towards normal. So this is the first phenomena. At the moment when it bend towards normal, due to the diffractions, so the white color light sun ray, it will split into the 7th color. The split into the 7th color is because of this dispersion. From the white color, split to 7 colors of light, which is a rainbow of light. Okay, so this phenomena causes dispersion. So why and how dispersions occur? Because all the different colors of light have the different wavelength. When they have a different wavelength, so when you're entering the when you have, because of the diffraction, so it will be diffracted with a different angle. Okay, so your SPN level, you don't really learn detail in these dispersions, so you just only have to remember because of the colors, different colors have a different wavelength. Therefore, when you experience the diffractions, it will be dispersed into the seventh color due to the different wavelength, different angle of the diffractions. All right. So when it comes to number 2 here, because at this moment, all the angle, incident angle of the different color here, all is more than critical angle of the water. Okay, more than critical angle of the water. So that's why total internal diffractions occurred at number 2. When the total internal diffraction occurred, right? So we come to the other side of the edge, so it will be slowly spread out. When the color, 7 color, it will be spread out wider. Then 4, when it comes to number 3, it will be diffractions again. So the angle will bend away normal. So that's why spread out with all the 7 colors. This is the formations of the rainbows. Okay. So means after the raining, if you want to see that rainbow, you have to make sure the positions of the sun, it must be behind you. Then only you able to see the rainbow. So basically, when you see the rainbow of the sky, you turn around your head, the sun on the behind you. Okay. So that is formations of rainbow. Okay, and applications. So my battery is very low now. Okay, so I'm going to finish this soon. Okay, so the applications of the total internal diffractions of light, if you're referring to my module, I have give you the comparison for this application of the periscope. One using prism, one using mirror. Okay, so mirror is based on the diffractions, of light, and the prism based on the total internal diffractions. So what's the difference between these two? Okay, from again you can see the result with the total internal diffractions prism, the image will be clearer. With the mirror, image will be not that clear compared to the using of the prism, because the mirror is based on diffraction. So the diffracted layer is behind the mirror. The front here is actually glass. So it means that the partials of the light is entering the glass. So it causes brightness is not 100% diffracted. But the total internal refraction, the brightness 100% diffracted. So that's why the image forming will be clearer for the prism. Right? Okay, and okay, so another one is the sparking of the diamond. Okay, so the diamond, why is do so many sparking inside it, so many shining? Because the light will be experience a few total internal diffraction when you're entering the diamond. Every diffracted total internal diffraction point here, it was make it have a sparking because it's like the light diffracted by the mirror. Okay, so due to that, the diamond have a special cutting angle, the shape. So is to make sure that no matter from which angle you view look at the diamond, it will always have a lot of the sparking due to the multiple total internal diffractions occurred. Okay, so basically the diamond is the optically denser glass lah. Okay, so but the ladies all likes the diamond. Okay, because they like the shiny sparking. Okay, so if you study chemistry, diamond just a commons lah. Okay, all right. Okay, so and then the diamond have a very small critical angle. It's about 24.4. So that's why the cutting shape of the diamond, to make sure that all the light ray enter, it will be more than 24.4 degree. All right. So okay, I think that's all for this. Okay, and then the last one, the most important one, application of the total internal diffraction is the optical fibers. Okay, so optical fibers, I think this one I stop here first. I will discuss a little bit more further on this one before I continue with the 6.3 lenses. So okay, so I think that's all for today lah. So optical fiber, you try to reach whatever notes given in the module first before I further discuss, and also in the textbook regarding this optical fiber. Okay, so try to read first. Okay, because SPM, one of the popular topic they will ask about application is about optical fiber. Okay, and the scientist invented this optical fiber. He got the Nobel Award. All right, he got the Nobel Award for the because of this invention for optical fiber. Because without optical fiber, today we don't have a high-speed internet. Okay, so it make a lot of change of our daily life. Okay, so this one I will discuss further next class lah. Okay, so that's all for this morning. Okay, thanks for joining the class. I will make announcement soon when is our next class. Most possibly will be the tomorrow morning also. Let me arrange first. All right. Okay, thank you.
Thank you, teacher.